Hello students, in this lecture we will find out the rotational vibrational spectrum of a diatomic molecule. In the last lectures we have considered vibration and rotation separately. Here we consider the actual case in which a diatomic molecule is simultaneously executing both vibrational and rotational motion. Since each vibrational level includes rotational levels, each vibrational transition must be accompanied by a simultaneous rotational transition. From Born-Oppenheimer approximation, if we excluding the electronic energy, the total energy will be rotational energy plus vibrational energy. The combined rotational vibrational energy in joules will be like this, and in centimeter inverse I am changing E as epsilon and the same expression. Here we know what is the epsilon vibrational and epsilon rotational. That is the energy levels of vibrational state and rotational state in centimeter inverse. And if we are combining this, we will get the energy levels of rotational vibrational states. That is Vj into J plus 1 plus V plus half into nu bar E minus V plus half the whole square into nu E bar into chi E centimeter inverse. Here you can see this is the expression for an anharmonic vibrating molecule. Actual molecule undergoing anharmonic oscillation will be a non-rigid rotor. Then in this expression, you must see some distortion constant, or at least one distortion constant D. But since it's a diatomic molecule, for a non-rigid rotor, you must have a distortion constant along with this expression. But for simplicity, we are avoiding the distortion constants in the rotational energy expression, as it makes a very minute change in the spectrum. So the combined rotational vibrational energy level expression will be this, where J and V are the rotational and vibrational quantum number respectively. V is the rotational constant, nu E bar is the equilibrium vibrational frequency of the molecule, chi E is the anharmonicity constant. Next, we can see the energy level diagram of vibrational level containing rotational energy levels. Since the vibrational transitions need more energy, it should be contained rotational levels, and we have dealt with this during our first introduction lecture. Now let us look the transitions of rotational levels between two vibrational levels. Here we are considering only two vibrational levels. Spectroscopically, normally double prime is used to represent the ground state and single prime is used for the excited state in all cases. Here, for the transition, first we need a selection rule. What will be the selection rule for the rotational transition? We know delta J equal to plus or minus 1, And the vibrational spectrum of the atomic molecule and harmonic oscillator, you know delta V equal to plus or minus 2, plus or minus 1, plus or minus 2, plus or minus 3, etc. But at room temperature, the considerable transition only will be delta V equal to plus or minus 1. That is from ground state to excited state. So we are considering the two vibrational states only, the ground vibrational state and the first excited vibrational level, where you can see different rotational energy levels in each case. The rotational levels are filled to varying degrees of population since they have less energy gap compared to vibrational levels. So the transitions also will occur with varying intensities. Now let's see the different transitions possible for a rotational vibrational levels. For delta V equal to plus or minus 1, we can expect transitions from ground state to the V double prime to V prime rotation, first vibrational level, where delta J can be plus 1 and delta J can be minus 1. That is, transition can occur from J double prime 0 to 1 transition is possible, 1 to 2 transition, 2 to 3, 3 to 4, that is, for these all transitions, J double prime becomes J prime becomes J double prime plus 1, that is 0 to 1, 1 to 2, also 0 from 0 it increases to 1, 1 to increases to 2, that is delta J is equal to plus 1, and we can also write it as J prime. J prime is J double prime plus 1. Is it? J prime 1 means J double prime 0 plus 1. Okay. And it will be useful for our next calculations. Next, another transition also possible, that is, rotational levels are very differently populated things. So as rotational levels have low energy gap, we can expect molecules in the ground vibration, second or third rotational level of ground vibrational level. Here also it can be possible. So that there must be transition from first state to the zero state. This first rotational level of the ground vibrational level to the ground rotational level of the first vibrational level. That is J prime 1 to J double prime 1 to J prime 0. Also 2 to 1, 3 to 2, 4 to 3, etc. And that will make delta J equal to minus 1. And the expression will be J prime is equal to J double prime minus 1. This much transitions are possible for a diatomic rotating vibrator. And then we can elucidate the spectrum. For that, we have to find the frequency of transition. That is, by calculation using this energy level, how will be the difference in energy for a transition? That is, from delta E, J double prime to J prime. That is, since different possibilities are there, we will give a general expression, J double prime to J prime. And here we are considering only a room temperature transition, that is from 0 to 1, and the difference in energy, which is in the upper state, J prime minus lower state delta E, E2 or E1 minus E0. That is that when we rearranging it, you will get the expression as delta E J B equal to mu 0 bar plus B into J prime minus J double prime into J prime plus J double prime plus 1 centimeter inverse. You must calculate it and should come to this expression where the mu 0 bar you should get as mu E bar into 1 minus 2 chi E. As chi is a very small quantity, we will be approximated it as mu 0 bar for simplicity. And for this transition delta J equal to plus 1, J dash become J double dash plus 1, and from the previous equation when we substituting for J prime, we will get delta EJV become mu 0 bar plus 2B into J double prime plus 1 centimeter inverse. And for delta J equal to minus 1 transition, you will get an equation having delta EJV equal to mu 0 bar minus 2B into J prime plus 1. Should keep in mind that here for delta J equal to plus 1, the lower energy state will be J double prime, and here since it is delta J minus 1, lower energy will be in the upper state J prime. We know frequency of rotational transition is 2B into J plus 1, where we have given J is the lower energy, lower rotational quantum number. Here also, here J double prime will be the lower rotational quantum number, here the J single prime will be the lower rotational quantum number. And the first transition will give rise to branches known as R branch, and the second will give rise to P branch. And in some rare cases, the transition J dash will be maybe equal to J double dash, that is delta J becomes 0. Delta E, delta epsilon JV become mu 0 bar centimeter inverse. That will not be an allowed transition and will not appear in the spectrum, but it can be possible transition. But since it is not allowed, it will not be in this spectrum. Now we have to see the rotational vibrational spectra of the atomic molecule. How the spectra would appear. Here, the Q branch or the central line that will not be appear, I am repeating, in the spectrum. It will be a blank space, since allowed transition will only give rise to considerable transition. And the branch that may get the center is known as band center or band origin, for which delta J equal to 0, that is 0 to 0 transition. From the J equal to J double prime 0 to J single prime 0, J double prime 1 to J single prime 1, that is delta J equal to 0 transition. For that transition, the mu 0 bar, it's a purely vibrational structure. It will be a pure vibrational structure. There is no rotational transition. It will be the pure vibrational structure, and it will become band center or band origin that will not appear in the spectrum. Next, for P branch, what will be the expression? mu0 bar minus 2b into j single prime plus 1. Here, single prime 1 to 0. The first transition is 1 to 0. That is 0. If we are substituting 0, we will get mu0 bar is here minus 2b. Here minus 4b. Here minus 6b. Here minus 8b. That is, you will have lines in the P branch 2b, 4b, 6b, 8b from the equilibrium vibrational frequency. For R branch, you must get mu0 bar plus the same 2b, 4b, that is, for this the lower stage z 0, 1, 2, 3, and you will get 2b, 4b, 6b, 8b, 12b, etc. And for Q branch, the lines at mu0 bar, lines will be at mu0 bar, and it will not appear in the spectrum. The lines to the low frequency side of mu0 bar is called P branch. It will be less than the mu0 bar, and high frequency side of mu0 bar is the R branch. Frequency increasing, less than mu0 bar will be P branch, higher than mu0 bar will be R branch. And since all are equally spaced, the distance between the lines always 2b centimeter inverse, both for P branch and for R branch. And you should also note one thing, that the two lines in the starting lines in the P branch and R branch will have a separation of 4b centimeter inverse. Since here is no spectral line, the first two lines in the rotational vibrational spectrum will be separated by 4b centimeter inverse, and the lines next onwards it will be 2b centimeter inverse separation. That you should keep in mind. Hence, here is about the vibrational, rotational spectra of diatomic molecule, by which we can find out the equilibrium vibrational frequency, rotational constant, etc., and the actual molecule undergoing anharmonic oscillation should give this type of spectra as it rotates also. Thank you very much, students.